This week we're covering chapter 6, and it's another week where we are covering an entire chapter in 1 week and not dividing it into two. So it's a bit of material to cover, but there is some stuff that we're going to skip over. So specifically page 156 to page 159, everything that is about concentration and molarity, we are not going to cover. It's not going to be on an exam or homework other than extra credit. So there is an extra credit homework assignment that is on molarity. If you want to do that, that's worth up to, I believe, 12 points of extra credit. And it's possible that some of that might end up as extra credit on the exam, but you are not required to do anything about concentration and molarity. There's also a section, page 160 to 161 in the book, that's called the role of buffers, and we're going to completely skip that section, and it will not be on any exam as well. I would also just kind of advise, there's some stuff that I'm not going to cover in as much detail in the book, and you're pretty safe just watching this lecture this week. Now, if there's anything that you are not totally grasping, go back to the book and read and give yourself another source, because that is really the best way to understand something. If you're not, is read it in a different format, or get it in a different format. But if there's things that the book is covering in more detail than what I'm covering in the lecture, then I'm not going to be putting it in the exam this week. And just also keep in mind, there's 3 weeks of material before the next exam. So the next exam will include chapter 6, which is 1 week, and then 2 weeks of chapter 7. So chapter 6 is only going to be about 1/3 of the next exam also. Okay, and it's a regular 50 point exam. So this chapter is titled Ions, Charged Particles in Solution. It's really, though, mostly about acids and bases, which is a specific attribute of certain ions. Okay, so this chapter could almost really, the title be changed to acids and bases, because that's what we're primarily going to focus on. We'll do a little bit about salts, but so why are ions important in food science? Why do we care? So we've talked about this before. Ions are charged particles, or particles that have an imbalance of electrons and protons. So they have a charge to them. And they do react to form ionic bonds. And when ions are put in a solution of water, they will separate from the bonds. And in that case, they might be classified as acidic or basic. Now, there are some ions that will not. For example, salt. So sodium chloride, salt. When that goes into water, the ions do separate from each other, and you have sodium ions and chloride ions that are suspended in the solution, but neither of those are acidic or basic ions, and so adding salt to water does not change the pH. Does not change the acidity or basicness, alkalinity of the salt, of the water. But some ions do. Okay. Ions contribute various attributes such as flavor, obviously saltiness when we, and we'll talk about what makes a salt, but salt is composed of ionic compounds. Also food safety. We use ions, specifically acids and salts, for food safety, and also palatability, how good something tastes. Okay, so an important thing to understand when we are talking about acids and bases is the ionization of water. Water will naturally, to some extent, separate itself into ionic parts. Not all of it will be separated, but when you just have a cup of water, some of the water molecules will separate into ionic parts. And so you have water and it can go back and forth, and it can separate into hydrogen ions and hydroxide ions. And so what's essentially happened there is that you have the two hydrogens and the oxygens. One of those hydrogens has broken off and it's left one of its electrons behind. And so now that hydrogen has 0 electrons because its atomic number is 1, and so it only had 1 electron to start with. Has 0 electrons, it has a positive charge of 1, and the hydroxide, which is what is left when it broke off of the water molecule, now has that extra electron, and so it has a negative charge of 1. Okay, but hydrogen ions, like I said, it now has no electrons, and so it will bind quickly with anything that it can, because that's not a happy state for it. If it is going to be very attracted to any negatively charged particle. Hence why it's going to go kind of back and forth between water and separating into ions, but also that hydrogen ion is attracted to the water molecule itself. So here it's demonstrating you have 2 water molecules, and what it ultimately will end up as in solution, because that hydrogen ion, you're not going to find it by itself in solution. It's going to associate itself with something else so quick, you're not going to find it in solution. But what you will find is the hydronium ion. So the hydrogen that broke off of, let me get my laser pointer out. The hydrogen ion that broke off of this oxygen, okay, is going to attach itself to this one, okay? And so that's what we see here, okay? So we have an oxygen now with 3 hydrogens, and this third hydrogen is the one that came off of here that left its electron behind, and so it has a positive charge to it. And so when it comes and attaches itself to this water, it's bringing that positive charge. And so this is called a hydronium ion, and it has a positive charge of 1. And then we still have that hydroxide ion that that initial hydrogen just left its electron there with it, and so it has a negative charge of 1. So what you are going to find in a solution of pure water is 3 compounds. You're going to find H2O, water. You're going to find H3O plus, the hydronium ion, and you're going to find OH minus, the hydroxide ion. Those are the 3 molecules that you're going to find in water. So now getting into what are acids and bases. So acids are any substance that produces hydrogen ions or hydronium ions when they are in a solution of water. Okay, so these are compounds that they will naturally release that hydrogen, or specifically what's going to happen is they're going to release that hydrogen ion, and that is going to bind with water to perform hydronium, right? And so we call those proton donors because hydrogen, the hydrogen ion, it doesn't have an electron. It does have a neutron, right? But it's just a neutron and a proton. And so you can almost consider that hydrogen just a proton, okay? There's the neutron there too, but from the proton-electron standpoint, it's just one proton, okay? And so we call those proton donors. So here are examples of common acids, and you see on all of these, they have extra hydrogens in there, okay? All of them have hydrogens. Now, just because something has hydrogen in it, does that make it an acid? No. Those hydrogens have to be able to easily break off and as hydrogen ions, but is a good indicator. Okay, so then bases, on the other hand, are substances that will produce hydroxide ions in solution. Okay, and so you look at these common strong bases in particular, you see that hydroxide is a part of all of them. And so, as I was talking about with sodium chloride earlier, ionic compounds, when they are in water, the ions will dissociate from each other and just be suspended in solution. And so you'll have sodium by itself in the water and the hydroxide. Okay, the sodium isn't going to have any kind of reaction that's acidic or basic, but this hydroxide will. Okay, so because this hydroxide ion is negatively charged, it is going to be attracted to protons, and so another word for bases is proton acceptors. Okay, they're willing to accept a proton. Now I'll point out these weak bases. These don't necessarily have hydroxide, but they are still bases for other reasons that we're not going to really get into right now. Okay, and then finally neutral solutions. In a neutral solution, you would have equal amounts of positive and negative ions. So if you have just pure water, there's going to be equal amounts of hydronium and hydroxide ions that are just naturally present in the water. And because one's not overpowering the other, it is neutral. Okay. And then finally, our last big key substance here is salt. And so when acids and bases combine, this is called a neutralization reaction. And so they combine, they neutralize each other, and now the product, as long as you combine equal amounts of the acids and bases, the product would be neutral and not acidic or basic. And that compound would have ionic bonds with it, and that is a salt. Okay, so continuing along here, so to be an acid or a base, it can also be a compound, an acid or a base, but not have any hydrogen to donate or accept. And there's just specific scenarios where it's very compound specific. Okay, but the key thing to know here, you're not going to need to know really any of the compounds other than the one that I'm about to talk about. But the key thing to know is that if the compound can accept electrons, then it's an acid. If it donates electrons, it's a base. Notice that this is exactly the reverse of the previous screen. So acids are proton donors. Okay, so they have a positive charge, and so they donate that positive charge. Well, if they have a positive charge, electrons are going to be attracted to them, and they will also accept electrons. Okay, bases on the previous screen, they have a negative charge, and so they are proton acceptors. And because they have that negative charge, they have extra electrons, so they're also electron donors. Okay, and so it's really two ways to say the same things. It's just whether we're talking about the proton part of the molecule or the electron part. Okay. And so the example, the single one that I want you to know that is not a hydrogen donor or acceptor is CO2. So carbon dioxide, when it is suspended in solution, such as in sparkling water. It accepts electrons, and so therefore the solution is acidic. So sparkling water is acidic. The mouth sensation that you feel when you drink sparkling water or Coke is actually the activation of pain receptors responding to the carbonic acid that is produced when the CO2 accepts electrons. And like I don't drink soda anymore, but I just remember like loving that burn as it would go down your throat. Um, but um, but yeah, and so even sparkling water, it's acidic, and that acid is actually not so great for your teeth, and it makes your teeth more susceptible to sugars and decay. The good news about sparkling water is you don't have sugar also there, but you think about colas, and so even diet colas, they have additional acid added. Okay, and then if you're not drinking a diet cola, if you're drinking a sugar version, you have additional acid and the sugar all wreaking havoc on your teeth and contributing to erosion of your tooth enamel. But just the CO2 in that is an acid and contributes to that. So, FYI. Okay, so pH is like the big word with acids and bases, and it shouldn't be too new of a concept to you. Um, pH actually stands for the potential of hydrogen, okay? And it expresses the degree of hydrogen or hydronium ions in solution. Specifically, it's a water solution, so it would be more talking about hydronium because hydrogen isn't going to be suspended in water, as we've talked about. And just kind of FYI, to help understand what the numbers mean, I find this helpful for me. The numbers actually express 10 to the negative x, x being whatever the pH number is, molecules of hydronium per liter, or hydrogen. So a pH 1 has 0.1 hydrogen or hydronium ions per liter. pH 2 has 0.01, okay? And so the pH 1 has the highest concentration of hydrogen or hydronium ions per liter, okay? The concentration just decreases from there. And so pH 1 is the most acidic, right? Because hydrogen and hydronium ions make something acidic. Okay, so pH 1 is the furthest acidity you can go. It's the highest concentration of hydronium ions. Then we go all the way down to pH 14, and this is literally, there are 13 zeros here, okay? And it is that, whatever that is in, I don't know, billionths or whatever, hydrogen or hydronium ions per liter. Now, conversely, it actually, if you are measuring pH, there's also a measurement called pOH, which would be the potential of hydroxide, and it's kind of the inverse of pH, and the concentration increases of the hydroxide ion. So pH 14 would have a hydroxide ion level that is the highest it can be, and pH 1 would be a super low concentration of hydroxide ions. And so you've probably seen a figure like this before. So battery acid is like so acidic it's almost pH 0. Stomach acid is around pH 1. Lemons, sodas are 3. And so for every value of pH that we increase, we are actually increasing the acidity, or once we get to the alkaline side, the alkalinity by a factor of 10. Okay, so soap, that whatever soap this is, like there's lots of different kinds of soap, so this is kind of a weird one, but this particular soap, if it has a pH of 12, it is 10 times more alkaline than this ammonia solution that has a pH of 11. Okay, so every increase of a full number in pH is a factor of 10 that you are multiplying it. Okay. So acids are below 7, bases or alkaline substances are above 7, and yeah. And the stronger the acid or base, these strong ones can cause severe burn, so you need to be careful. Okay, so how we measure pH. So the most accurate, precise way to measure pH would be using a pH meter, which is a fancy piece of lab equipment that is designed to read all of the hydrogen and hydroxide ions. Okay, another way that we can measure pH is with titration. And so the way that works is you have an unknown acid or basic solution, okay? And you put indicator in there, some kind of substance that you know is going to change color once you hit a certain pH. And then you slowly add a standard solution. This example here shows sodium hydroxide, which is a base. But if you had an unknown base, you could add a standard solution of an acid, such as hydrochloric acid. Okay, and you are measuring this as you add it. Okay, and you're adding it slowly, drop by drop, until your indicator that is going to change color once you hit a certain pH changes color. And so then you'll read the final volume to know how much of the base or acid that you added, and this is called a neutralization reaction, and you'll be able to then calculate what the initial pH was of your unknown here. Okay. Then there are various indicators that you can use that are less accurate, less precise than the pH meter or titration. So most precise would be the pH meter, then titration. Next would be pH paper, if we're looking at indicators. So pH paper is like a paper like this. The paper itself is kind of an orange color, and then you dip it into the solution, and it changes color, and then you hold it up to this like color key here, and have a good estimate of what the pH is. Okay, there are also organic dyes. If you were in my chemistry class last year, we did some stuff with red cabbage, and just the natural substances in red cabbage will change color based on the pH. So low pHs, we're going to have like a red to pink color, neutral, purple to blue, and then when we get more alkaline pHs, that changes from green to yellow there. So everything so far here gives you an indication of what the pH of your substance actually is. The last one, litmus paper. So this is the least precise, accurate, just the least precise method that we have available. All litmus paper will do is tell you, is it an acid or is it a base? And so you actually have to have blue or red litmus paper to start with. And so if it's a blue litmus paper and you stick it in an acid, it will turn red. If you stick red litmus paper in an acid, it will not change color. And if you have red litmus paper and you stick it in a base, it will turn blue. If you put blue litmus paper and stick it in a base, it won't change color. Now, problem with this is both of these, if you just stick them in a neutral solution, they also will not change color. So red litmus paper in a neutral solution will stay red. blue litmus paper in a neutral solution will say blue. And so the only thing it can tell you is if what you're sticking it into, what you're submerging it in, is an acid or a base. Okay. It doesn't give you a real degree of it, like the pH paper does. Okay. So, overview of acids and a couple things that we haven't talked about yet. Okay, so we've already talked about how acids will produce hydrogen or hydronium ions in solution. We haven't mentioned this yet, but they have a charge to them, right? And you can refer to that as an electrical charge, that, electron or lack of electron charge, all right? So that's a positive charge. They are proton donors, as we've already talked about. They're electron acceptors. The pH is less than 7. Okay, and then finally, when we're talking about foods, acids tend to taste sour, and we've talked about how they will turn litmus paper red. So this page is a good notes page for understanding all the things about acids. Okay. So, okay. Bases, right? They produce hydroxide ions in solution, but overall they have a negative electrical charge, opposite of acids. They are proton acceptors, as we've talked about, or electron donors. And so if they don't produce hydroxide ions, they are still electron donors. So not all bases produce hydroxide ions, not all acids produce hydrogen ions or hydronium ions, but the key thing is that they are either proton acceptors or electron donors, and vice versa, proton donors or electron acceptors. Okay, pH of bases is going to be greater than 7. Taste-wise, so acids taste sour, bases will taste bitter, and they will also have a slippery feel often. Okay, so you think about soap, right? It's slippery, and they will turn litmus paper blue. Okay, now you'll notice one thing I noticed with this little graphic is fertilizers in both of these. But you can have fertilizers that do different things. So on the bases side, we have ammonia as a fertilizer, and then on the acid side, we have nitric acid, which is also used as a fertilizer. Both of them are sources of nitrogen. Okay, so now let's talk about acids and bases in the body, specifically in digestion and in our bloodstream. So saliva has a fairly neutral pH. So pH 6.5, maybe slightly acidic, but it can also be in a normal range and be neutral. So pH 6.5 to 7.5 is all neutral. Then once the food enters the stomach, it is exposed to stomach acid. So hydrochloric acid has pH of 1.5 to 1.7. And there can be a normal range to that. So like this has like upper stomach is 4. So before it reaches the hydrochloric acid is 4 to 6.5. But then the lower stomach, where there's a lot more hydrochloric acid, is 1.5 to 4 pH. And so this is going to be a lot of the breakdown of your food. Now, interesting point here, all right? Like stomach acid, it is naturally extremely acidic, all right? This is hydrochloric acid. It's one of the strongest acids. And so kind of a point here is that like eating acidic foods is not going to increase the acidity in your stomach, because whatever food you're eating is not pH 1.5 to 1.7. That would hurt to eat. So the way heartburn actually works is those greasy or acidic foods actually cause there's a sphincter at the bottom of the esophagus where it reaches the stomach, and it causes that sphincter to relax. And so sphincters keep things closed. And so if that sphincter relaxes, it opens it up, and now stomach acid can come up through the esophagus and like hurt, be painful in your esophagus and even sometimes up to your throat as like acid reflux. And so that is actually the cause of heartburn. All right, then once the food exits the stomach, it's going to go into the small intestine. And the first section of the small intestine is the duodenum, or duodenum, however you want to pronounce it. And the pH there goes quickly back to near neutral, okay? And how that happens, because that food coming in there is acidic, right? It's coming from the very acidic lower stomach, is that the pancreas is excreting a juice that is pH 8. And then you're also having bile that is excreted from the gallbladder, which is located right there. So here's the gallbladder, here's the pancreas, and here's the entrance to the small intestine, okay? And so they're both like excreting these more alkaline substances that the goal there is to lower the pH and get it close to neutral, because from the small intestine, the nutrients are now going to enter the bloodstream, okay? So the beginning of the small intestine, we're getting that pH down to neutral, and then once it's in the small intestine, it's going to enter the bloodstream. And the pH of blood is pH 7.4, so close to neutral. Okay, now role in food preservation of acids and bases, and then we'll talk about salt. Okay, so most bacteria thrive at pH 5.0 to 7.5. Notice I've adjusted that pH from what's in the book. I think the book had just 7.0, maybe. I did adjust it because it's a little bit off. But 5.0 to 7.5. So most bacteria are what is called neutrophilic, which means they prefer a pH that's close to neutral. There are some bacteria that don't, but the one bacterium that the book talks about, and we're going to learn more about different spoilage bacteria and pathogenic bacteria in a later chapter, but we will go through this, is Clostridium botulinum. Okay, it's a really important bacteria for food preservation, because it kind of has a certain limit to where it grows, and but also it's really important in canning, because Clostridium botulinum loves no air. So under normal conditions, botulinum spores are actually on most fresh food surfaces. They are naturally in the dirt, and so you're going to find them all over vegetables. You're going to find it in the air. It's everywhere. Okay, and generally, Clostridium botulinum is harmless, because the spores only grow and produce the toxin under certain conditions. So the bacteria is found as in form of spores, which is kind of like, it's a kind of bacteria in a hardened shell. It's not in its ideal environment, and it's just like trying to stay alive. Okay, it's not going to try to reproduce. It's just like, I'm just going to sit here and get through this, and maybe someday I'll find a condition where I can grow and be happy. Okay, and those conditions are the absence of air. So they live environments with no oxygen. And there also has to be low acidity. And so by low acidity, I mean the pH is greater than 4.6. Okay, so if that bacteria gets happy, then it will come out of its spore form. And during that process, it's going to produce a neurotoxin. And as it grows, it produces this neurotoxin. Okay. So as the name sounds like, it causes botulism, um, and it's just not a good thing. Um, Foods with a pH that are less than 4.6 are considered high acid food. And so no matter what, even when you take all the air out of it, as in canning, uh, the botulinum bacteria is not going to like it. It's not going to get happy and come out of its spore form and produce that toxin. Okay, so if you have like uh, jellies because you have fruit that are high acid or tomatoes, those things are very safe to can at home just with boiling water. Okay. However, foods that have a pH that are greater than that, these are low acid foods. And so if you do not make an effort to kill these spores before you're finished canning, then once you have now canned that food, you've taken all the air out of it, that spore is going to be happy because it has a pH that it can grow, and now there's no air. Um, and and so then it can grow, it can produce a toxin, and then and then someone can unknowingly eat that toxin, um, and could die, or be very seriously made ill. And so these foods that are low acid, um, they are going to need a pressure canner. And um, pressure canners can heat food to a higher temperature because when we add pressure, the boiling temperature of water increases. And so we can heat the food with a pressure canner to a high enough temperature that it will actually kill the spores. Boiling water will not kill these spores from this bacteria. Um, and so the goal is to get the temperature up to 240 degrees Fahrenheit. So 212 is normal boiling temperature. With pressure, we can get it up to 240. And for a specific period of time, which is going to vary based on the food and what the exact acidity is of the food and that food's properties. And there's tables that you can look up. But the key thing here is that the acidity plays a big role in what temperature we need to cook what temperature we need to can at, um, so that we can kill this very abundant in the environment bacteria that, fortunately, you probably haven't heard much about because our food safety system in the US is such that canning is a very, very well-developed process commercially. But if any of you have done canning at home, hopefully you know a little bit about this and what is safe to can with boiling water and not. Another option that you could do in place of this is pickling. So like a cucumber, that is not a high acid food, but you pickle it and you lower the pH. Well, now you don't have to put it in a pressure canner, right? Because now the pH is at low enough that that Clostridium botulinum spore cannot grow. So separate from canning, low pH foods, foods that are naturally low in pH, such as yogurt or buttermilk, the reason they naturally last longer is because they are at a pH below that which most bacteria thrive. Okay, so continuing with food preservation, so yeasts are a different kind of microorganism, right? They're not a bacteria. They're their own little category. So yeast require a pH of between 4 and 7 to grow. So pretty close to what the ideal bacteria pH range is, but it does go a little bit lower. Down all the way to pH 4, that yeasts are happy. Now, yeast can sometimes be a good thing. Sometimes we want the yeast to grow, like when we're proofing bread or when you're making wine. But sometimes yeast are actually spoilage. So if you've ever seen this on your lunch meat, there's like little dots. It almost looks like, and maybe that's me because I was in the meat industry, it almost looks like shavings, like just like little pieces of like fat that somehow got dispersed on the meat. But no, these are like little yeast buds, yeast colonies that are growing on there. If you've ever seen that, it's not dangerous. It's spoilage. It wouldn't hurt you if you ate it. It just probably wouldn't necessarily taste that great. But and this meat is that great pH for yeast, and so it will grow on it. And then of course we use yeast for winemaking. And so it's good to know what pH you need to be at, because if you get below that, your yeast aren't going to grow and aren't going to do what you are desiring. Okay, mold has a much wider pH range. Mold can grow at very acidic pHs, all the way from 2 and then up to about 8.5. So it's pretty hard to stop mold from a pH perspective. And so this is why, jelly, this is what this is a picture of, is like a jam. You can have that in the refrigerator sometimes for a very, very long time. All of the sugar content in jelly makes it so that bacteria aren't really a concern because there's low water activity, and I think we'll learn about that later on, but maybe even next chapter. But mold doesn't need a high water activity, and it doesn't need a neutral pH. And so even though that jelly is a fairly low pH, mold is perfectly happy to grow on it. So if you get mold in your jelly, it's going to grow. But then of course in other cases we want mold to grow. Mold isn't as hard to control because from a pH perspective, like making sure that our pH stays right, because the range is so wide. But it's good to know at what point it would stop growing and not do what you're wanting it to do. And so this is blue cheese. Okay, and then finally, talk about salts. Okay, so salts, when we combine acids and bases, we have a neutralization reaction and we produce salts. And they preserve food by reducing the available water for microorganisms. Okay, and so a good example of that, today would be the country ham, which is not something people buy very often anymore, but these hams are preserved purely through salt. And so they are not cooked. They might be smoked. But that is not heated, right? It's just smoked at a low temperature. But they're mostly just salted and dried. Okay, so now let's go into baking. Okay, and specifically we're going to talk about chemical leavening agents. So leavening is making dough rise. Okay, it's the increase in gases that make a dough or batter rise. Okay, so chemical leavening agents are ingredients that are added to baked goods to lighten or aerate to make it rise, the finished product. So the key thing here is that these chemical leavening agents are going to contain a base, and then when that base combines with acid, a neutralization reaction occurs, producing salt, water, and carbon dioxide gas. And this too should be down here. little typo here. So CO and then subscript 2, not superscript. Okay, so our 3 that we're going to talk about are baking soda, baking powder, and ammonium bicarbonate. Okay, baking soda, which is called, which the chemical name for that is sodium bicarbonate. Okay, there are 2 possible reactions that can occur with baking soda. Okay, the first is you have baking soda and you add an acid, such as lemon juice, vinegar, sour cream, buttermilk, or cream of tartar. And so what that looks like, here we have sodium bicarbonate. We've added acetic acid, reacts to form sodium acetate, water, and carbon dioxide. So this is just an example. The products would change depending on what acid reactant you have here, but you will always have water and CO2. Okay, and so that CO2 is going to make pockets of CO2 in the batter or dough, and ideally you get that product started cooking before it can escape, and so as it cooks, that matrix around it hardens, and you're left with a nice little air pocket in your product. Now, you can also use baking soda without acid, because it does also have a reaction that produces CO2 with just using heat. So here we have sodium bicarbonate, we've heated it, and it reacts to form carbon dioxide, sodium carbonate, so instead of sodium bicarbonate, it's sodium carbonate, and water. Only problem with this is that sodium carbonate has a bitter flavor and a yellowish color, so you cannot use a lot of it if you're doing this. And you might want to have it in a recipe that disguises the flavor and color a little bit. That it's okay if it has a yellow color, and maybe it's sweet enough that it doesn't matter if it adds a little bit of bitterness. So when this is used, it'll be used in recipes that have acidic ingredients, quick bake recipes like cookies, muffins, pancakes, and recipes that benefit from browning, because there is a browning reaction that occurs here. Now with this and with the next one with baking powder, not over mixing is going to be really important. Because if you have this reaction, this happens very quickly. Okay, and when you add acid, if you've added acid to vinegar before, or sorry, you've added baking soda to vinegar before, right? It happens. The reaction happens very quickly. It happens quickly in your baking too. It's just at a much smaller scale. And so if you are stirring this after this acid reaction has taken place, then you are creating a way for all of these CO2 bubbles to escape. Okay, and so what you'll end up with is a product that is not fully risen, that is flat, because you added the baking soda and acid for nothing, because the CO2 isn't even in it anymore. Okay. The other chemical leavening agent that you would use at home would be baking powder. And so baking powder is actually a combination of baking soda, dry acids, and a filler. Okay. And so it's basically the same kind of reaction as the other, but you already have acids in it. So now what is unique about what we have at home is the double acting baking powder. So it's not just baking powder, but it's double acting. And so it actually has 2 dry acids. And the first one reacts as soon as it's exposed to moisture. And the second one actually only reacts with the baking soda when it's heated. Now, the filler that we use, it's actually only in the container to absorb moisture, because if you've had this baking soda and the acids in direct contact with each other, and they get wet, what's going to happen inside this can of baking powder, right? They're going to react, and then your baking powder will be useless. Um, and so it acts kind of as a preservative. And so most commonly there's just cornstarch that is also in your baking powder to do that. The okay, I should have mentioned on the last slide with the baking soda. So cream of tartar is one of our acid options. And so that's what is here, potassium bitartrate. It is an acid, okay? So the reaction here is sodium bicarbonate is reacting with the cream of tartar that is in the baking powder, potassium bitartrate, and it performs sodium potassium bitartrate plus carbonic acid. So this is all in the first part of the double acting baking powder, but it has 2 steps. Okay. So there's an initial reaction that forms carbonic acid. Okay. And then the carbonic acid breaks down to form water and carbon dioxide. Okay. And so this first part of the double action produces about half of the carbon dioxide in double acting baking powder. Okay. The other half is the heat reaction. So here we have the baking soda, the sodium bicarbonate. It's reacting with this other acid that it's only going to react with heat. So sodium dihydrogen pyrophosphate. Okay, and it's going to produce sodium pyrophosphate, carbon dioxide, and water. And this sodium pyrophosphate, unlike the heat reaction that is just only with sodium bicarbonate, it's not going to affect the flavor in a negative way when we do that. Okay. Again, so this double acting baking powder, it protects you a little bit because you're still going to have this happening after you mix and put it in the oven. But it is still important to make sure that you are not over mixing after step 1 because you're going to allow the CO2 to escape. The other thing is to don't delay baking. So as soon as you get your batter mixed, it needs to go in the oven, because if you're just letting it sit and not going in the oven, that CO2 can just naturally slowly escape the batter. Okay. Okay. And so this produces the other half of the carbon dioxide that's produced with double acting baking powder. Okay, the third one, we're going to talk about this super briefly because it's not really as important either commercially or domestically at home. But there's another chemical leavening agent, ammonium bicarbonate. It produces ammonia, carbon dioxide, and water. Now, ammonia is a gas, carbon dioxide is a gas, and water is just water, right? And so its products, when you cook, there's none of it is left in the product, in your baked good, unless you put it in something where it couldn't escape. Okay, so like if you're whatever you're making is too dense, too big, and it couldn't escape, well, then it's going to be left in there, and ammonia does not taste good. And so this is only used in thin products with large surface area, such as crackers and cookies. But the reason why it's not as important is it's not going to be used at home because it's only available to commercial bakers because it's releasing ammonia gas. And ammonia gas isn't really a great thing to be having in your house. And so it requires a special ventilation system for the gas. And it's really not even used very much commercially anymore. I think maybe it used to be, but I couldn't find a single product when I was looking that had it listed in the ingredient statement. And it is supposed to be if they're using it, even though none of it except the water ends up in the product. So probably, if I had to guess, the reason it's kind of been phased out even commercially is because of the ventilation requirements. Because like, yeah, and ammonia is not a safe thing to be breathing in. And so it does require that special ventilation system, and probably for safety reasons, and maybe cost, companies have done away with it. Okay, so how pH affects batters. This is super interesting stuff. Basically, the more basic the batter or dough, the flatter or coarser the product it produces. So if you think about an angel food cake, that is super, super airy, fluffy, soft, right? It requires high acidity to get that character. Okay. Also, so some reasons for that, egg whites have a more stable foam when they're acidic. Flour is whiter when it's acidic. Recipes, and so the recipes for angel food cake will generally call for a lemon juice or cream of tartar to achieve that acidity in it. And so if you don't have that acidity, it's not going to be as airy, and it won't be as white. Okay. Now on the other hand, chocolate cakes are better if they are basic. So pH closer to 8. So it's not super basic, but it is basic. And it's been shown that the cocoa will have a deeper, darker color at a higher pH, and it also contributes to a smoother flavor. And so this picture I found Googling pH in chocolate cake, and somebody did an experiment. And so on the left, we have a chocolate cake that is cooked with baking powder and baking soda and no other acids. Okay, so it has like the cream of tartar that's in the baking powder, but no other acids were added to the mixture. And then on the right, it's exactly the same recipe with these changes. Instead of milk, they used buttermilk. And then they also added a tablespoon of vinegar to the solution, to the mixture. And so the batter on the left, the pH when they measured it was 8, and on the right it was a pH of 6. Okay, so really the only difference in these two cakes is the pH. It's made with the same kind of cocoa powder, same flour amount, sugar, all that, but pH. And so yeah, like a higher pH results in a darker chocolate cake. Okay, so eggs and pH. So in-shell eggs, the shells are porous, and over time, as that egg ages, carbon dioxide will escape. And so, as we learned earlier, carbon dioxide is acidic. So when you lose carbon dioxide, it makes the eggs more basic. And I mentioned in the previous slide that acidity helps the egg foam retain, like egg have a good foam. Okay, so fresh eggs have a pH of 6.4 to 7, and older eggs can have a pH all the way up to 9.7. So it can gain quite a bit of alkalinity, and so fresh egg whites are known to trap more air. They produce higher meringues and lighter angel food cakes. You'll also see that in older eggs, the egg whites are just more runny. They don't kind of maintain their shape as well. You can overcome some of this by lowering the pH with cream of tartar, and you'll see cream of tartar added to a lot of like meringue recipes and stuff. Yeah, there is some wisdom about if you're a meringue maker, you want to use aged egg whites for better meringues. And I just want to note that that's not talking about how old the egg is. What they actually do with aged egg whites is they remove the egg white from the egg. They separate the egg white and the yolk, and then they let those egg whites sit refrigerated for several days. And that is aging the egg whites. And essentially, all they're trying to really achieve with that is they are removing some of the moisture. They're letting the egg white dehydrate just a little bit and become more concentrated. And that is what, with the old cooking wisdom, helps make a better meringue. And it's really just because the egg whites are more concentrated. So conversely, old eggs are really good for boiled eggs, hard-boiled eggs, because that membrane, with all that CO2 release, things shrink up and the membrane kind of detaches from the shell and it releases better. So old eggs are easier to peel when you are hard boiling them. But it's also my trick for peeling hard-boiled eggs is pressure cook steaming them. That makes it easy too. Okay. Then see, so pH and fruit maturity. This is our last slide here. Thanks for hanging in here with a little bit over an hour long lecture for this week. Okay, so acids, as fruits ripen, the acid level increases, okay? And this actually improves the juice quality because along with that, you get better color and and it increases the sugar content. The acids work to change parts of the fruit to be sweeter, okay? The ideal pH is going to be different for each fruit. But I mean, if you just think about it, like blueberries, the worst blueberries are like bland, not tart, just yuck, right? But usually that tartness, if it is starting to pick up some tartness, it comes with some sweetness, right? In the fleshy part of the blueberry, right? And I'm sure you've experienced this with all kinds of fruit. It's just like the tartness and sweetness wasn't there, and it's usually just because they were picked when they were underripe. And the color might have developed, but the flavor did not, and it was not great. So with winemaking, for example, the pH is extremely important. We've talked about how yeast is important and with pH and affected by it. But the pH is going to vary and the sweetness is going to vary by grape variety. Citrus are unique in that they really don't ripen once they've been picked. Some fruits do, but some definitely do not. And so when growers are figuring out when to harvest citrus, if they're doing a good job, they're checking the pH to determine when is the right time to harvest. When are they going to have good ripe fruit overall from their harvest, and it not just be like, I'm sure like we've all had just like bland oranges that were not good, and it's because they were harvested too early. So, and that is it for this week. So we will see you later.